We can also use knowledge of solubility and KSP to separate a mixture of ions. So for example, on the screen here, we have I- and chlorine ions here. And what we're going to be doing is adding a reagent that forms a precipitate with just one of the dissolved ions, but not the other. So our precipitating ion or our precipitating reagent is going to be Ag+. And as Ag+ is added to this mixture of ion, one of these ions are going to precipitate out first. The question becomes, which one? Now, to figure out which one is going to be precipitating out first, we look at the KSP value. The KSP value of what? The KSP value of the potential solid that's going to be formed. So for Cl, that means we're going to have AgCl that's formed. And the KSP for AgCl is 1.8 times 10 to the negative 10. Next, we have AgI that has the potential to be formed. And the KSP for AgI is 8.3 times 10 to the negative 17. And the pattern that we see is the one that has the lowest KSP will precipitate out first, usually until it's almost at saturation, meaning the QSP value is almost equal to the KSP value. And as we see here, we see AgI forming a precipitate. So AgI will continue to form a precipitate as it gets closer to saturation, and then and only then will excess Ag+ be able to form a precipitate with the chlorine. Because remember, the AgI is going to precipitate out first. Another thing is since the AgI is going to precipitate out first, it needs a less or a lower concentration of Ag+ in order to form a precipitate. So you don't actually need much of the precipitating ion to continue on. And this entire process of separating ions through differences in the solubility of their compounds is called selective precipitation. And again, we must have a precipitating ion or reagent that's going to be added to our mixture. And once we take our precipitating ion and of course form the solid with our overall anions in solution for this example, then we can again have the dissolution equations in equilibrium for these solids. And then of course we can use the KSP expressions to get the concentration of Ag+, for example. And again, the one that's going to have the lower KSP should also produce a lower concentration of the precipitating ion that it has to use. And sometimes two or more equilibrium systems are controlled simultaneously to separate one metal ion from another. So for example, if S2- is our precipitating ion here, it's added to this overall expression equilibrium, we have the ability to shift the equilibrium dissociation of this weak acid. Of course, we have the ability to then shift or change the autoionization of water. And again, if we are adding this S2- as a precipitating ion, it then has the ability to affect solubility. So of course, we can add all these systems together and it can be layered and become more complicated. But for our course, this is what we're going to focus on here, which is simply going to be selective precipitation. So let's go ahead and get into an example. Okay, we're back at the Avengers compound and we are separating ions by selective precipitation. So it says a solution contains 0.021 molar of Cl- and 0.017 molar of I-. A solution containing copper-1 ions is added to selectively precipitate one of the ions. At what concentration of copper-1 ion will a precipitate begin to form? So how will we be able to answer that question? First, we have to figure out which one of our potential ions are going to precipitate first based on the KSP expressions, right? And then once we know that, we can figure out our copper ion concentration. And whichever one has the least amount, we can say, well, that makes sense, because if they're going to precipitate out first, then they should have the lowest amount or least amount of that precipitating ion, which here is copper-1. Okay? And then says, what is the identity of the precipitate? They're just simply saying between these ions or whichever solids they form, which one is going to precipitate first, and therefore be the identity of the precipitate that we will see first. Okay? They also gave us KSP value of CuCl and a KSP value of CuI. So essentially, we have our precipitating ion, which is copper-1 or Cu+, and it's going to be added to a mixture with Cl- and I-. So the question becomes, okay, are they going to form or create a precipitate? Well, we know that because we're already given the KSP values. So yes, this was form CuI, and yes, this was form CuCl. So the next thing we want to do is create our dissolution equations for these particular solids and in equilibrium, and then go ahead and match the KSP values that are given to those expressions. Okay, so for CuCl solid, it's going to be in equilibrium to form Cu+ and Cl-. The KSP expression is going to be Cu+ times Cl minus, which is equal to 1.0 times 10 to the negative 6. Number 2, we have CuI solid in equilibrium to form Cu plus and I minus, with the KSP is equal to Cu plus multiplied by I minus, which is going to equal to 5.1 times 10 to the negative 12. And so can we answer one of our questions, which is what is the identity of the precipitate, or can we answer at what concentration? Right now, we can't answer the concentration of Cu plus. That's what we're going to be solving here. We're going to be solving for these concentrations here to see what it is, so we can answer that portion. But as far as the identity of the precipitate, we can answer that right now just from previous knowledge. We know that the one that's going to have, or the ion that has the lower KSP, is going to give us the precipitate first. And so automatically, when I'm looking at CuI or Cul, this has the lower KSP value. So yes, the identity of our precipitate should be CuI. Now we're going to verify that CuI by the concentration of copper. We should verify that the concentration of copper we get after our calculations should be lower than what we see for CuCl because it precipitates first. So let's go ahead and get our calculation. Essentially what we're doing is solving for Cu plus here. All right, so to solve for Cu plus concentration, since we already know that our precipitate should be CuI based on the lower KSP, then we're going to take our KSP expression. It's equal to Cu plus multiplied by Cl minus. We divide by Cl minus. And so therefore, Cu plus is going to equal to our KSP value, which is 1.0 times 10 to the negative 6, divided by the concentration of Cl minus, which is given as 0.021 molar. When we divide this, I get 4.8 times 10 to the negative 5 molar. Now again, we're doing these calculations to verify that CuI also has the lower concentration of Cu plus that's needed for precipitation. So let's do that. In order to solve for Cu plus here, we're going to take our KSP value again, 5.1 times 10 to the negative 12, and divide it by the concentration of I minus, which is given as 0.017 molar. When I divide those two numbers, I get 3.0 times 10 to the negative 10 molar. So now we can write our answer. Our answer is going to be, okay, what precipitates out? Or what's the identity of the precipitate? Meaning, what's going to be the first precipitate formed? That's CuI. What is the concentration of copper ion that a precipitate begins to form? Meaning, what's the least amount of copper I can use before I see precipitate? And that is 3.0 times 10 to the negative 10 molar. Let's go ahead and get to the next concept, folks.